This video is about relations and functions. Be sure to take good notes while you're watching this video, and if at any time you need to pause, rewind, and replay a portion of this video, be sure to do that. A relation is a mapping or pairing of input values with output values. In other words, it's a set of ordered pairs. The domain is the set of input values. The first component of the ordered pair is an element of the domain. The range is a set of output values. The second component of the ordered pair is an element of the range. There are different ways to represent a relation. One way would be to represent it using set notation, a set of ordered pairs. An example would be the set -2, 2, the ordered pair -2, -2, the ordered pair 0, 1, the ordered pair 3, 1. In this relation, there are 4 elements, there are 4 ordered pairs. Another way to express this relation would be by using a table of x, y values. The ordered pair -2, 2, -2 for x and 2 for y. The ordered pair -2, -2, -2 for x, -2 for y. The ordered pair 0, 1, 0 for x and 1 for y. And then the ordered pair 3, 1, 3 for x and 1 for y. Another way to represent this relation would be by using a graph, by actually plotting these ordered pairs in the xy plane. X and y having be my horizontal and vertical axes. The ordered pair -2, 2, -2, 2. The ordered pair -2, -2. The ordered pair 0, 1. And the ordered pair 3, 1. In this example, they're asking us to identify the domain, the range for the following relation, and then graph and create a mapping diagram for that relation. We're looking at 4 ordered pairs inside of our relation: 5, -2, -3, -2, 3, 3, and -1, -1. The domain is the set of the first component in each of the ordered pairs. And so the domain is going to be the set that includes 5, -3, 3, and -1. I'm using the first component in each of the ordered pairs to go ahead and create the set for the domain. The range is going to be the set of elements that gives me the second component in each of the ordered pairs. And so -2, 3, and -1 are the numbers that I'm using for my second components. Again, the range comes from the second component in each of the ordered pairs, my range values. In asking me to go ahead and create the mapping diagram, I'm going to lay out my domain numbers in a vertical column. I'm going to lay out my range numbers in a vertical column, and then I'm going to go ahead and create the mapping diagram. The -3 is mapped onto the -2. The -1 is mapped onto the -1. The 3 is mapped onto the 3, and the 5 is mapped onto the -2. I'm simply drawing a line mapping the domain element to the appropriate range element. A function is a special relation for which each input has exactly one output. In the first example, I'm looking at a set of ordered pairs. The ordered pairs 4, -2, 4, 2, 3, 3, and 1, 2. This is definitely not a function, because if you take notice here, the element 4, the domain element 4, gets mapped onto 2 different range elements. It gets mapped onto -2, and it also gets mapped onto 2. Therefore, this is not a function, this is simply a relation. In the next example, the four ordered pairs, 4, -2, 5, 2, 3, 3, and 1, 2, is definitely a function because each of those domain elements get mapped onto one and only one y value or range element. Even though the 5 is mapped onto the 2 and the 1 is mapped onto the 2, those are different domain elements mapped onto the same range element. We're allowed to do that and still be a function. The stipulation for being a function is that every domain element maps onto only one range element. And so our second example is definitely a function. Another way to determine whether or not something is a function is by using the vertical line test. A relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. If we take a look at the graph on the left-hand side, and if I use a vertical line and move the vertical line through the graph, I can see that the red line intersects the blue graph in only one location at each point along the blue graph, along the blue curve. That means that the graph on the left is definitely the graph of a function. I'm going to take the vertical line and move through the graph on the right. As I move through the graph on the right, notice that the red line definitely intersects the blue curve in more than one location. I have 2 points of intersection along the red line when I move through the blue curve. That means that this graph is definitely failing the vertical line test. It's not crossing in only one place, and so the graph on the right is not a function, it is only a relation. We will be graphing equations of functions in two variables. Those equations are going to take on the form y is equal to mx plus b. The independent variable is going to be the x value. The x value will be the input variable. It will come from the set that is the domain. Those values typically sit on the horizontal axes in a coordinate plane. The y in the equation will be the dependent variable. It will be the output variable. It will be the second component in our ordered pairs. And those values come from the range, typically sit on the vertical axes. Linear functions can be written in the form y is equal to mx plus b, where the m and the b are going to be constants. In other words, the only thing that will change in the equation will be the x and y, and the ordered pair will stipulate what x is and what y is. If we're using function notation, almost the same. Function notation simply says f of x is equal to mx plus b, where f of x actually represents the output value, or the y. We're going to graph f of x is equal to 1/2 x plus 1. Our m is equal to 1/2, our b is equal to 1, definitely taking on the linear format. And this graph is definitely going to look like a line. That's what linear functions look like. So I'm going to be choosing some values for x, and I'm going to be plugging them in to find my values for y. And again, I'm going to be plugging them into 1/2 x plus 1. My domain is going to be the set of all real numbers. That means I could choose any x that I'd like to choose, but I'm going to pick x's that are going to be relevant to my picture, relevant to my coordinate plane. And so I'm going to choose some x's that are sitting right here in front of me, close to my origin. And I'm going to start by saying, let's go ahead, let's let x be equal to -4. When I let x be equal to -4, I'm going to be taking that and plugging into that x coordinate. And so y is going to be equal to 1/2 times that -4 plus 1. And when I complete the arithmetic, 1/2 times -4 is equal to -2. -2 plus 1 is going to give me -1. This is going to give me the ordered pair -4, -1. And so one of the elements in my relation, -4, -1, I'm going to go ahead and graph -4, -1. I'm going to pick another x value to plug in so that I can get a general idea of what this graph is looking like. And I'm going to choose my x a little bit wisely to make my work a little less difficult. In other words, I know that I'm going to be dividing by 2, so for my x values, I'm going to pick some even numbers. I'm going to go ahead and move on over to x being equal to -2. And so I'll take 1/2, multiply it by -2, again plugging in for x, and then adding 1. 1/2 times -2 is equal to -1. -1 plus 1 is going to give me 0. And so I have the ordered pair -2, 0. Again, I'm going to go ahead and pick another x value. I'm going to pick 0 for x. When I plug in the 0, it turns into 1/2 times 0 plus 1. 1/2 times 0 is 0, plus 1 is equal to 1. And so I have the ordered pair 0, 1. And I'm going to pick just maybe one more point that's going to help me go ahead and create this graph. I'm going to go on over to where x is equal to 2. And so 1/2 times 2 plus 1. 1/2 times 2 is going to give me 1. 1 plus 1 is equal to 2. And I have the ordered pair 2, 2. I have enough points now on this graph where I'm going to go ahead and connect them. Knowing that this is a linear equation, it's going to create a nice straight line for me. And when I connect these points, I'm going to go ahead and have that line right there. Every single point that sits on that line will satisfy the equation y is equal to 1/2 x plus 1. Now I'd like you to go ahead and try one. Hit pause on the video and see if you can graph f of x being equal to 2x plus 1. When you're done, restart the video and we'll go ahead and check your work. When we're graphing f of x being equal to 2x plus 1, again, we're going to go ahead and let f of x be y, and so we'll plug numbers in for x, and we'll get y by plugging into 2x plus 1. Again, I could pick any x that I want to, right? The domain is going to be all of the real numbers, and so I'm going to pick x's that are relevant to my picture. I'm going to say, let's go ahead, let's start with x being equal to -2. When I let x be equal to -2, I'm going to be plugging into the x coordinate, right? So it'll be 2 times -2 plus 1. 2 times -2 is equal to -4, and -4 plus 1 is equal to -3. I have the ordered pair -2, -3. And so I'm going to be graphing right about there. I'm going to let x be equal to -1, and so 2 times -1 plus 1. 2 times -1 is -2. -2 plus 1 is -1. And so -1, -1, right about there. I'm going to plug in 0. When I plug in 0, 2 times 0 plus 1 will be equal to 0 plus 1, so 1, 0, 1. I'm going to plug in 1 for x, and so 2 times 1 plus 1. 2 times 1 is 2, plus 1 will give me 3. I have an ordered pair 1, 3. And one more, I'll plug in a 2, 2 times 2 plus 1. 2 times 2 is 4. 4 plus 1 is equal to 5. I have the ordered pair 2, 5. I'll say about right there. And then I'm going to go ahead and I'm going to connect my points and know that my graph is the straight line, right, the blue straight line. If you feel the need to revisit any of the concepts presented in this lesson, remember that you can watch the video again as many times as you like. We will be working on the practice problems from this lesson in class, where we can discuss and answer any questions that you may have. Thank you.